Hello, everybody. Hey, this is going to be gravitational lecture number 4. And we're going to progress to energy considerations of objects essentially in the universe. Now, a quick review of what we talked about yesterday, which was primarily potential energy. So, gravitational potential energy is negative g mass of the Earth times the mass divided by the radius. Now, to me, this is just, it's weird, right? It's weird. And to kind of go back or to kind of extend it a little bit further out, is if we have, let's say, the ground, and we're going to have a table here, and we're going to drop a ball. Okay, so just think about this. We're just going to drop a ball. Okay, now how much potential energy? How much potential energy do we have here? Now, before, you guys, we talked about this is just equal to mgh. Okay, where this is h final and this is h initial. Now, the reason we can just say mgh is because we conveniently call this 0, right? So then h final just becomes h. Okay, so that's how much gravitational potential energy that we have. Now, well, what if we made the ground 0, and now we had this 1, and let's take, for example, we're going to have this at 2. Okay. Now, when we did it the first time, when it was 0, this would have been 1, and we would have had, for a 1 kilogram object, we would have 1 times 9.8 times 1, which would give us 9.8. And that would be 9.8 joules. Well, what if now we change to be 0 right here? So essentially what we're doing, we're saying mg delta h, which would be mg h final minus h initial. So we would have 9.8 times our final position would be 2 minus 1, and that would be 1, and that would be 9.8 joules. Okay, so essentially what we can say here is we can make our 0 any place we want. Now, even if we were way up here, okay, we're going to make h equals 0 right there. And if h is equal to 0 here, we're just going to say that this is negative 2 and that this is negative 3, right? So how much gravitational potential energy do we have from here to here? Okay, well, now our final position is negative 2 minus a negative 3, and that would be plus 3 minus 2 plus 3 is 1 times 9.8 is 9.8. Okay, so essentially there's another proof that it doesn't really matter. Now the problem becomes when we are talking about the universe. Where do we make h equals 0? So here it was all good because this 9.8, this g, that g is near the surface of the Earth, so it's 9.8. Even if we go way up on Mount Everest, in which the acceleration due to gravity would be less, I think on the order of like 9.77, which still round to 9.8. Okay, it is less, but essentially all around 9.8. But remember, as we start going farther and farther away from the center of the Earth, like 2 Earth radii is going to be 9.8 divided by 1/2 squared, which would be 1/4. So it would only be 2.45. So it's changing when we're talking about big distances, okay, like in space, the solar system, the universe. So the question is, where is there a place that is equidistant from every place in the universe, okay? And we talked about this yesterday. and that place is infinity, Okay, now I'm going to kind of come back up here and change this. And if you may remember from our equation, that was 1 over r final minus 1 over r initial. And that came from that integral. It came from the integral of force dr. And you can look at yesterday's lecture there. Now, if we make our initial radius, if we make this infinity, okay, so where we're calling 0 is at infinity, all right, then 1 over infinity obviously just goes to 0. And now we don't have to call this our final. We can just call it whatever radius it is, okay? And now we can call that radius, and now all this goes away, and we have our potential energy. We have our potential energy at any one location, right? So now if we want to know our delta U of G, okay, so now we can say negative G M E M times 1 over r final minus 1 over r initial, right? And so now, as long as we know those two radii, then we're just going to take the difference. And the key here, and this is the part that's counterintuitive, is we get a negative. But remember, if we're going from someplace that is closer to someplace that's farther away, we're going to say, if this is a smaller number, it's going to be bigger. This is going to be bigger than if we have a larger number, in the denominator. So when we subtract, this part's going to be negative, and that's going to cancel out that negative, and we're going to give a positive answer for the change in potential energy, aka we're going to go up. Okay, if we go up, this radius is bigger than this radius. This quantity becomes negative times this negative, and we end up with a positive delta U, which makes sense, but it's that negative that's really kind of weird. All right, so now what we would like to do is we're going to add in kinetic energy. Okay? So let's talk about mechanical energy. And we know mechanical energy is equal to kinetic energy plus gravitational potential energy. Now, whenever we talk about mechanical energy, what are we forgetting? And what we're forgetting is internal energy, temperature, okay? The oscillations of the chemical bonds going back and forth because they're vibrating around. We are ignoring all that. We're just talking about essentially this macroscopic stuff. So if I take this ball, okay, and I throw it through the air, okay, when I throw it through the air, we can say that it goes through a parabolic curve. Now, what we're ignoring when we're going through this parabolic curve is we are ignoring the air resistance. And we talked about this earlier in the year. We're ignoring air resistance because it's pretty complicated. What happens when we're actually moving through the air, we're having to create a path, and we're moving molecules. We're moving molecules out of the way. And essentially what's happening is we're making those molecules move faster. And if we're making those molecules move faster, we're changing the temperature. And if we're changing the temperature, we're changing the internal energy. But a lot of this stuff that we're talking about, when we're talking about universal gravitation, we're talking about the moon and the sun and Venus and Mars, right? So if we have an object and we're moving it through space, there's no air resistance, okay? There's only going to be air resistance around the surface of the Earth or other places, right? Now, we're still ignoring that air resistance, but it becomes less apparent. But essentially, because we're doing that, we can kind of say that this mechanical energy is the total energy, So what do we know? All right, we know that kinetic energy is 1/2 mv squared. And we know that this gravitational potential energy is negative G MEM over R. Okay. Now again, here I'm using the illustration of gravitational potential energy around the Earth. We could do it around the Sun or Venus or Jupiter or something like that. If we're doing it around the Sun, this mass changes to the Sun or Jupiter or whatever we're talking about. This mass here, okay, this is the mass that we're actually moving. And the example that we're going to use is we're going to be moving a satellite. Okay, yesterday's question of the day before's question of the day, today's question of the day is all talking about a satellite. And I think I made it 5,000 kilograms, 5,000 kilogram satellite. We're also talking about a geosynchronous orbit, which we made calculations early, and I will bring those numbers back in. Okay, so this is our total energy. Now, what I would like to now talk about is the total energy of an object in orbit, the total energy of an object in orbit, okay? And I'm gonna review or kind of give this conceptual idea of this, because I don't think I did this before. And to give you perhaps a more conceptual idea of this, if I take this ball and I throw it, right, it's going to go in a parabolic curve. Again, ignoring air resistance, okay? Now, if I want to take this ball and throw it around the Earth, okay? So here is the Earth, right? So I might go up on a hill. And throw it. And let's make this hill even bigger, right? Obviously, we are exaggerating. Now, if I throw it, it's going to go in a parabolic curve. If I throw it faster, it's going to go still in a parabolic curve, but it's going to get a greater distance, okay? If I throw it fast enough, okay, it's going to keep falling. It's going to be falling, but it's not going to hit the Earth because the surface of the Earth keeps going away, right? It keeps falling away, so we're throwing it fast enough. Now, what's causing it to hit to the ground? It's going to be gravity, right? But if we have this force of gravity and it keeps pulling it towards the center, we are going to have an object. We're going to have an object that is in orbit. It's going to be in circular orbit, okay? Now, we talked about this before, but we're going to be a little more specific to what the energy is, okay? So what's causing this, what's causing that object to go in orbit? And the answer is gravity, okay? So we're going to have the force of gravity is equal to big G. Again, we're talking about the Earth, mass of the satellite, or whatever it might be, R squared. But since it's going in a circle, it's going to be mv squared over r, all right? Now, we already saw this concept twice. The first time we talked about, and I think it was the lecture number 1, we used this concept to determine the mass of the Earth, which we ended up with about 6 times 10 to the 24th. And then we also used the same concept, and we used that to develop Kepler's third law, or really to prove Kepler's third law for an object. And a reminder of Kepler's third law is T1 over T2 squared is equal to R1 over R2 cubed. Okay, so that came from this. But this time, okay, this is R, not R squared. Okay, so this R is going to cancel out. And what I'm going to do is I'm going to divide both sides by 2. I'm going to divide both sides by 2. Now, why am I doing that? You'll see in a minute. But the question is, can I? And as long as I do something to both sides, it's still going to be an equation. It's still going to be equal. Okay? So I'm going to get this equal to G MEM over 2R is equal to 1/2 mv squared. 1/2 mv squared. So we can say this right here is equal to kinetic energy. Okay? And so what we're going to do here is we're going to substitute it right in there for kinetic energy. And we're now going to have big G, mass of the Earth times mass divided by 2R, minus big G MEM over R. And so essentially what we've got here is we're going to have positive 1/2 minus 1 whole. Positive 1/2 minus 1 whole. And obviously that is equal to negative 1/2. Okay, so we're going to have negative G MEM over 2R. Okay, so this right here is the energy. This right here is the energy of an object of a mass in orbit. That is the mass of an object in orbit. Now remember, it's in orbit because it keeps falling, right? It keeps falling and falling and falling, but it's falling at the same rate that the Earth is giving away due to the fact that it's a sphere, okay? So we could have an object up here, okay, and it is going to be in orbit because it keeps falling. It keeps falling around because gravity keeps pulling it down, all right? And that would be in a circular orbit. Now, as it turns out, and I'm not proving it here, but negative G MEM over 2A, okay, is also the energy of a orbit, where this is an ellipse, and this is the major axis. Okay, so whether it's radius or semi-major axis, whether it's a circular orbit or an elliptical orbit, it's still going to be the same. It's still going to be the same. All right, so we have another equation for that energy. Okay, so now we are going to look at our question of the day for the day, and that is going to be how much energy does it take? How much energy does it take to move that 5,000 kilogram satellite from the surface of the Earth to a point where it's in geosynchronous orbit? Now, remember yesterday's question of the day. Yesterday's question of the day was just to calculate the change in gravitational potential energy, okay, which is just going to be this equation 1 over R final. That R final for a geosynchronous orbit, which was the answer to the day before's question of the day, was 4.23 times 10 to the 7th meters. And this original position would be the radius of the Earth, starting on the surface of the Earth. And this is 6.37 times 10 to the 6th. Times 10 to the 6th. And I think the day before it says what altitude is a geosynchronous orbit? The actual altitude is going to be the difference. It's going to be the difference between those two, which ends up being just a tiny bit less than 36,000 kilometers. Okay, so geosynchronous orbit is way up there. Okay, so now I'm going to kind of erase some of the stuff, and we're going to talk about that energy in terms of that sort of logic. So let's go through this. All right. So we're going to have conservation of energy. So we're going to have energy before equals energy, which is going to equal to energy afterwards. Energy before is equal to energy afterwards. Now, for my example here, we're going to take something from the equator, and we're going to move it out so that it is going to be 1,000 kilometers above the surface of the Earth. So how much energy does it take to move it from the surface of the Earth at the equator and bring it out to a point where it's in orbit at 1,000 kilometers above the surface of the Earth? Okay, so our energy afterwards is going to be negative G, mass of the Earth times the mass of the satellite, divided by the radius of the Earth plus 1,000 kilometers. Okay, that, from what we talked about, that's the energy of a object in orbit. Okay, now what do we have before? Okay, we're going to have the work. In order for us to move it from the surface of the Earth up to that point, it's going to take energy. So we're going to have to do work. Okay, but it's going to have kinetic energy, and it's going to have gravitational potential energy. Okay, well, what's the gravitational potential energy? The gravitational potential energy here is equal to negative G MEM over the radius of the Earth, right? So slightly different than that, not as high. The kinetic energy is going to be 1/2 mv squared. And the difference between all of this is going to be the amount of work, which is how much energy it requires. Okay, so how fast, you guys, how fast are we going? How fast are we going on the surface of the Earth? Because we are spinning about our axis, right? We are spinning about our axis. So what is our tangential velocity? What is our tangential velocity with respect to our rotation? So now if we think about the Earth, it's rotating, and we're going to have the equator. So right there, now velocity is going to equal to distance divided by time. How far do we go? And how long does it take us? So I'm going to use 1 day, okay? And we're going to go 2 pi r divided by our period, which is going to be 2 pi times 6.37 times 10 to the 6th. That's the radius of the Earth, divided by 24 hours. But we don't want hours, we want seconds. So 60 minutes in an hour, 60 seconds in a minute. So that's going to be 3,600. Okay, so that's going to end up with being 463 meters per second. Whew. Okay, so again, we're going to have 1/2. You guys, we can use 5,000, right? We could, whatever the mass of the satellite. I'm going to use 5,000 because that was the mass of the satellite in our question of the day. So we're going to have 5,000 times 463 meters per second. You guys, that right there is over 1,000 miles per hour. Just due to being on the surface of the Earth at the equator, we're going over 1,000 miles per hour, okay? Minus big G, mass of the Earth, times the mass divided by the radius of the Earth. Now, you guys, I am going to plug these numbers in here, okay? But I am first going to take these and bring it to the other side, right? So we're going to end up having work is equal to negative g mass of the Earth mass divided by the radius plus 1,000 kilometers, okay, minus a negative, so that's going to be plus big G mass of the Earth times the mass divided by the radius of the Earth, which is less than that, okay, minus 1/2 mv squared, okay. Now we know that that is our 1/2 of 1,000 times 463 squared, all right? So you guys, I'm going to plug those numbers in here, kind of going upwards. So work is going to be equal to, we can factor out a G MEM, and that means we're going to have, well, let's say negative, and now we're going to have 1 over 6.37 times 10 to the 6th plus 1,000 kilometers. You guys, 1,000 kilometers is going to be 1,000,000 meters, which is 1 times 10 to the 6th. 6.37 times 10 to the 6th plus 1 times 10 to the 6th is going to give us 7.37 times 10 to the 6th. All right? So that's going to be this part plus 1 over 6.37 times 10 to the 6th. Okay? And now we're also going to have this minus 1/2 mv squared. And I'm going to kind of get rid of this so I have room. Okay. Negative 6.67 times 10 to the negative 11th, which is G. 5.98 times 10 to the 24th times 5,000, okay, times, bear with me here, you guys, I am going to do this calculation in my calculator. So I'm going to have 7.37 times 10 to the 6th, and I'm going to flip that over, so I'm going to say inverse. And this is going to be we need this is going to end up being minus, and this is going to end up being plus, and that gets rid of this. Let's see. This goes plus and this goes minus when we distribute that negative. Okay, so then we're going to take inverse minus 6.73 times 10 to the 6th inverse. And we are 2.13 times 10 to the negative 8th, okay, times 5,000 times 5.98 times 10 to the 24th times 6.67 times 10 to the negative 11th. And we are 4.25 times 10 to the 10th joules, okay, minus 1/2 of 5,000 times 463 squared. $5,000 times 463 squared equals, that means we're going to have 4.2 times 10 to the 10th. 4.2 times 10 to the 10th joules. All right. So you guys, that gives you kind of a perspective on how much energy it takes to take that 5,000 kilogram satellite and just move it from the surface of the Earth just to 1,000 kilometers. 1,000 kilometers. And now we're basically saying, in the question of the day, I'm asking you to raise it to 36,000 kilometers. 36,000 kilometers. Now, we can't just take this. We can't just take this and multiply it by 36, because as we go higher and higher, the force of gravity is getting less and less. We cannot just multiply it by 36,000 because we are gravity is getting less and less as we get farther away from the Earth. All right. So this is basically that sort of same format that you're going to use for the question of the day. All right. So one more concept, which is escape velocity. So if we're sitting here on the surface of the Earth, okay, and we want to go into orbit, okay, that's essentially what we're asking in this question right here, okay? But what if we want to get out of the bounds of gravity? Essentially, we're going to go to infinity, right? We're going to go to a spot where it completely have no gravity pulling on us. All right. So now what we have here, okay, is we're going to have 1/2 mv squared, okay? This is going to be kinetic energy plus potential energy, which is minus g, mass of the Earth, m over r. This is going to be the radius of the Earth. And this is going to equal to the potential energy at some distant place where there is no gravity, okay? Now, where is that place? That place is at infinity, because when you are an infinite distance away, there is no gravity. What is infinity squared? It's still infinity, and 1 over infinity is still 0. So this goes away, right? So now we're going to take this negative gm m over r and bring it to the other side. So we're going to get 1/2 mv squared is equal to positive g, mass of the Earth, m over the radius. And now we're going to solve for v here, okay? This m is going to cancel out. This 2 is going to come out, so we're going to get v, and this is going to be the escape velocity is going to equal to the square root, because it's just square, of g, 2g. 2g comes up. Let me rewrite that. 2g times the mass of the Earth divided by the radius of the Earth. Okay. Now, if we were at some location that was above the surface of the Earth already, then we would not need to go as fast, because we'd already be going a certain distance if we were orbiting at that spot, right? So this is the equation for the escape velocity, and in this case, it's to get away from the surface of the Earth. So if we wanted the escape velocity of Jupiter, we would put the mass of the Jupiter and the radius of Jupiter, okay? So that gives us your escape velocity. Now, I am giving, in today's question of the day, it's asking what is the escape velocity, and all you get to do is plug in the numbers for the Earth, and you will have that. All right, ladies and gentlemen, that is it for this lecture.